So good morning, everybody. I'm Jon Handler, Director of Solutions Architecture at AWS. And today we're going to talk about how AI/ML is changing information retrieval, especially with a kind of emphasis on natural language, right? So as soon as we started writing stuff down, we needed to go find that stuff, right? So you can go all the way back to ancient Sumer, where the bureaucrats were like stamping stuff into the clay tablets, and they built indexes of the clay tablets that were the tax records or what have you. Later, you have Callimachus, is a Greek in the Library of Alexandria. He created this thing called the Panakes. This is an index of the scrolls that were in the library, right? So all of these things, in modern times, we've been doing card catalogs with more and more science about how to organize the information, how to make it easier to go find stuff, right? I don't know if, now we have the web, right? But I don't know if anybody here has been to a library and had to go look something up in a card catalog, and there are the subject matters that the librarians decided and all of that. Ultimately, even at a library, you needed to go talk to a librarian, right? The librarian could actually understand what you were saying and help you find the thing that you needed, right? So now we have this whole hype cycle boom in AI/ML with large language models giving us generative and also embedding capabilities to work better with natural language. So this has brought the rise of sort of chat interfaces, chatbots. If you look at the process of information finding, it's becoming more interactive through these kind of chats, the ability to carry conversation through the interaction. The time span has changed from single shot to getting a little bit broader window, right? And the interface has become more natural language. So, as we do search and as we think about search, natural language now becomes a main access. So does that mean we're going to get rid of all of the 10 blue links, single shot matching? Definitely not, right? There are search situations where you know what you want. It's the ML654-7 pipe fitting that goes from 1/8 inch to 1/4 inch. You just want to look that thing up and buy it, right? That kind of query we're going to continue to have. At the same time, we're going to have this more interactive, natural language driven query where essentially you're talking to a librarian, right? So as we look at this space, I'm going to walk through kind of lexical search, the basics. We'll talk about vectors. We'll talk about how you do vector-based querying. And then hopefully I'll get to a demo. So the basic idea in terms of lexical search, you have words that are units of meaning. And they run from the very concrete to the very abstract. The words, as you specify to a search engine, you're specifying your intent through words that, again, capture some form of semantic meaning, right? You express your purpose through expressing natural language into a text box, along with other stuff. Yes, there's facets. Yes, there's other stuff, right? Search queries, again, express that, right? And the idea of lexical search is we're going to match words to match that meaning, and we'll retrieve documents based on the meaning matches the meaning, right? But words are our unit here. So the more matches are better. If some document in my catalog matches tons of words in the query, that's better. And if those words are very discriminating across the corpus, the very unique words, those are more valuable. So this is the whole kind of idea behind lexical search. So I have some information goal. I have some means of specifying that information. The text, the facets, geo information, all of that represents my information goal. I send it to OpenSearch. OpenSearch has coded some set of documents that potentially can match, and OpenSearch's job is to figure out some similarity and send out ranked stuff that matches my information goal. So how do we do that? So the first thing we do is we encode our information into search documents. Probably all familiar, search documents are JSON with a set of fields and values. The fields provide individual matching for these units of meaning, right? So in this case, this is from the Amazon product question and answer data set. This is a particular question, should I go for small or medium, 5'8" and pretty thin? And then it has a set of answers to that question, along with some product information. In creating this, I created a chunk by putting together all of the text. So when we do lexical search, we want to prep to match that text. And the point of the preparation is to preserve the semantics of the words and to collect like semantic units into single terms that represent that. And we do that with analysis and stop words and stemming and synonyms. So if we have Miss Kobayashi's Dragon Maid Toru cosplay dress outfit, our analyzer then is going to take that and apply rules that, again, preserve the meaning, but reduce the set of tokens so that the matches are easier. Stemming, we bring to a common form. Runs, run, running, all go to run. Stop words, we remove words like a and the. These are not particularly valuable for matching, so we just throw them away. Except when a long time ago, I was working on an e-commerce engine, and I don't know if you know, there's a British band called The, and proved really difficult for us to retrieve that one. So you have to handle that one specially. Anyway, and then we add synonyms, because synonyms, again, provide us these groups of meaning that enable us to match those. They all work at the token level, and they enable us to match to the meaning of the term. Under the covers, then, we take all of the terms in the text. We create an index. Index maps a single term onto the set of documents that contains that term, right? The set of documents is called a posting list, and that we pass all of that data through analysis to get indices per field that point at the posting list. So when we query, I have an example here. We have two documents. We have Miss Kobayashi again, and we have a very soft silicone vinyl stuffed PP cotton body baby. It's a stuffy, right? My query is cotton washable clothes. Intuitively, Miss Kobayashi ought to match that, right? So the first thing we do is we pass the query through the same analysis, because if we're creating an index with a particular set of terms and we're querying with a different set of terms, we're not going to match the right stuff. Analyze the query. That makes it possible for us to match, right? So we take this cotton washable clothes, comes cotton washable cloth. We then, and washable without an E, we then go to the index and we look up each of those terms. So in this case, I made up an index here. You can see we have cotton, we have washable, we have cloth. Those give us the set of potential matches. We then have to apply the query logic to come to the single set of documents that matches all or the union of the query terms, right? So the merge here, we take our three posting lists, these sets of numbers. By default, apply an intersection across them. That means and. So and is intersection, must be cotton and washable and cloth. And we get the single answer, which contradicts what I said. It's 38. So, and that is just a mistake on my part. That's not this. Apologies for that. So we default use intersection. In fact, we can also use union. This gives us a broader set of candidates, which we then use scoring to bring the right stuff to the top, right? So we have cotton washable cloth. If we do an or on top of that, it gives us all of these possibilities. Then we rely on scoring to say which of those is the best possibility, right? So when we do scoring, again, as I said, there are two main ideas. One is, how valuable is each of these query terms? So that's represented by what's called IDF. That's the inverse of the document frequency. And that says if I the more times I appear across the corpus, the smaller that number gets. Then I have the term frequency. That's how much it occurs in this document, right? So here I just randomly assign some values for cotton, washable, and cloth. And I have the occurrences within these two pieces of text. I multiply them out to get the score, and that gives me the sorting 2238. So 22 does come up on top. All right, so this is how search works, lexical search. In the scoring, here's the hairy function that we actually use, OKP-BM25. This captures those ideas in terms of the inverse document frequency, the term frequency, and a number of normalizing terms that reduce the impact of lots and lots of matches that take into account the document length and then take into account how many times it occurs in the document, right? So we have the basic idea is TF-IDF. We add a bunch of weighting stuff that makes it work a little bit better empirically. So this leaves us in the typical lexical search kind of framework, right? You go query, you get some results. Are you happy with the results? Yahtzee. If you're not happy with the results, then you may be frustrated and just give up. But more often than not, what you do is you go back and write your query again and try some different words, right? And so we're all trying to play this guessing game with our technology. So, as you know, we have a lot of hype around vectors, and vectors come in and give us a different way of interacting with the information, right? So why vectors? Well, large language models, some ML models called large language models, loosely, more specifically transformers, they can capture the meaning of words or blocks of text. They can emit vectors that put these into a multidimensional space, and we can do matching based on nearest neighbor. And related words and concepts cluster together. So what is a vector? Well, a vector is a quantity. Like, why vectors, right? So everybody's talking vector embedding, right? How do these things work? So a vector is a quantity with magnitude and a direction, right? So here's a sample vector. It's on an XY axis. You have 7.21 at 56-degree angle, right? So the X and Y actually could mean anything, right? For instance, the Y-axis could correspond to orange. X-axis could correspond to apple, right? And we could represent then apple as a vector on the X-axis, right? It wouldn't have any component on the Y-axis. So starting a while ago, 15 years ago, we started to do one-hot coding. So one-hot coding, we have a place in that multidimensional vector for each concept. Like I have an apple is one of those numbers. I have orange is another of those numbers, on and on and on. Everything had one slot, right? We still use this. Some ML techniques still do one-hot. But what you don't get is generalization, right? So I can't say, if I say like apple plus banana, what is that? Or if I say color red plus apple, what is that? Or color red plus fruit, because I'm only allowed to have a 1 in some position, right? In this case, like each axis then is representing one concept. So one thing I can do is shrink down the set of terms. In other words, reduce the set of axes. And typically with sparse coding, we typically have about 30,000. So we reduce the set of terms down to about 30,000, keeping most of the axes at 0 with some at some positive number, right? So if I take this, I encode it sparsely, you can see as we squash down tokens, we have some weird kind of terms in there. Some of them are recognizable terms, but we're keeping this ability to have some generalization through loosening the restriction on it has to be 1 or 0, right? So this maintains some semantic information, but we also have a much reduced token set. The dimensions then much less than the number of corpus, and then some generalization, right? So with sparse coding, we maintain some of this ability to match exact terms. Dense coding, we throw away all the original terms, and our axes then, like we had in the one hot, we had the bajillion axes. In this case, our axes are learned to be some set of we don't know what, but that are the concepts within the original corpus of text, right? So in this case, we could have red, yellow fruit, and apple is red fruit, and banana is yellow fruit, but it's not that straightforward. This is all learned by backpropagation, right? So each dimension adds capacity to do discrimination between different concepts. Neural networks, backpropagation is how we learn these things. We don't have direct introspective way to say, what does that dimension mean, right? But it manages to generate meaning. In case you've never seen one, there's a big vector. It's so, like we talk about these embeddings and it's kind of mysterious and really it's just a big array of numbers that represent points on some axis, right? Generalization is high, but then you have the problem of overgeneralization or hallucination, right? So if you send to a text generating LLM any kind of prompt, it'll make up an answer, right? It's just statistically producing words. And so this is actually the sort of breaking point or how you have to contend with this problem. Generalization is good, but you get hallucinations. It is a highly complex space, incredibly nonlinear. You have n dimensions, which gives you millions of parameters, billions of parameters to characterize that space. And you need a complicated function, and that's what backpropagation is learning. So taking these kind of lexical and vector concepts back into the search space, really the ways that this comes together is around natural language. For me, the way I understand it, it's really about how we're coding language and how we're using that to reference particular documents to do matching. So we have new paradigms. We have our sparse models that generate sparse vectors that provide a good way to do retrieval. We have a multimodal. So now beyond text, I can do images. I can code those into that space. We have hybrid search. This seems to be emerging as kind of the most important thing. As we talked about the hallucinations and the sort of ability to generate from, the discrimination between very concrete and very abstract, applying kind of lexical, which gives you very concrete, semantic, which gives you very abstract, and mixing those results together actually turns out to be a really good strategy. And then conversational is kind of one of the places that we're going. So the basic idea in bringing all of these new paradigms, we have our database of stuff. We use LLMs to create vectors, and there's a whole prep phase in terms of building chunks of data, figuring out diagrams and other things, bringing all that information together. It gets encoded. I come with my information goal. I have words. I have some structured information. Maybe I have some images. I'm then going to pass all of that through vector models to create a point in that big vector space, which I'm going to find the neighbors for, right? And then I still get back ranked stuff. But again, for me, this is about language. It's like, how do I specify what I'm looking for? Right? So we keep talking about vector similarity. If you have this multi-dimensional space and we project all of that messily into 2 dimensions, which is hard to do, you get something kind of like this. This gives you the concept, right? You end up with roughly clusters of related concepts in that big multi-dimensional space. And that means that if it's a similar document, it's coded near the other similar documents, right? So when you want to find a match, you project your query into this space, you find the nearest neighbors, that gives you your match. In OpenSearch, we have our neural plugin that helps with this process. The normal sort of phase of events, if you're not doing this with neural plugin, you always take your source document, you create some chunks, You send it off to your model, maybe Bedrock. That gives you an augmented document that has one or many vectors that represent that document. It goes in a KNN index. Excuse me. On the query side, you take your user query, you pass it through the model. That gives you a vector. You do a KNN search, and that gives you search results. Neural plugin makes it easier by passing the documents out for embedding and by passing the query out for embedding. So it just is a little bit of a syntactical sugar that makes it easier to use. When you use it, then you need an ingest pipeline with the neural plugin. The ingest pipeline sticks to your index, and every document that comes for indexing, you send it to this pipeline. The pipeline passes it off to the model based on the model ID. On the search side, you also have a search pipeline. This enables you to, in this case, take a hybrid query that's run against both lexical and vector and combine it with arithmetic mean, combine the scores. So there's a normalization in the scores. Just schematically, hybrid search, again, you have your NLP search pipeline that does the combination. Your query looks like that. It just says hybrid. Actually, the hybrid does not require you to run lexical and vector and 2 queries only. Hybrid query takes up to 5 clauses and applies the arithmetic or normalization and all of the post-processing. So even if you have multiple vector queries, multiple lexical queries, you can run them through hybrid to do blending across them. For sparse, you define your pipeline. Oh, this is the index. So you define your index. You say, I want to use a sparse pipeline. You specify a rank features type field for that index, and that will take the sparse encoding. You send a chunk of text in, and it gets, well, that's the field. On the ingest pipeline side, same thing. Really, you just have a sparse encoding processor that you apply in the ingest pipeline, and that lets you do the coding. On the query side, it's a neural query. You're running against the chunk embedding field, and again, this will go do the sparse coding, run the query. Right. Multimodal, again, very similar story. I just wanted to run all these by you so you could see that the machinery is actually not that difficult, right? Especially if you're using neural. So on the ingest side, we're doing multimodal. We specify a model, and then which fields for the text embedding, which fields for the image embedding. Oh, sorry. And then on the query side, oops, there we go. And then on the query side, you just send in the 2 embeddings, and it does the query for you. So we have also a conversational search as part of OpenSearch. This enables you to simply set up for RAG, basically. And if you don't know, RAG is retrieval augmented generation. You have a little chat interface. You send text. The OpenSearch in this case goes and looks up in your index documents that provide a context that make it easier to, well, that reduce hallucinations, right? So you send in these search results to the LLM. The LLM then is able to tell you real stuff, not hallucinations. You also have a conversational memory built into OpenSearch. So with the memory ID, you simply specify that memory, and then that becomes part of the context that goes to the LLM as well. So fingers crossed. Am I doing on time? Pretty good. Fingers crossed, we are going to demo this. Pay no attention to the keyboard interrupt. So I thought I'd just walk through a little bit of code. This uses the OpenSearch client. The OpenSearch client, we have lovely client libraries for OpenSearch, including a Python client. We do need to enable the memory feature. We do need to enable the RAG pipeline. And then we have trusted connector endpoints where we're going to send the data. So that's the setup. We have here the connector, which is not fitting the full screen. So this is an example of connector. The connector, we have blueprints in the repo. ML Commons repo, I think. These blueprints enable you basically to set up the connector. This tells the connector what to do, including credentials here. This is credentials for me for Bedrock, parameters that I'm sending in, or that the plugin is sending in, and then action it's going to take, in this case, predict. Super important, the pre and post processors. So that happens under the covers, but the request body enables me to get in there. I could try to hack around with this, the prompt, but we just passed the prompt in. Then we register and deploy the model. So then you just send this as a connector. We're going to add a pipeline for search. That's going to be a RAG pipeline. So it's this response processor, retrieval augmented generation, conversation demo. And then here is the model ID that comes from the connector. This is the field that I want it to use for providing the LLM with context from the search results. And then here's a user prompt and user instructions. In this case, so again, it's Amazon PQA data. This is a set of questions and answers. So what I did here is I actually used the questions for retrieval, right? So I'm coming to this thing, say it's my librarian, I want to talk to it, I want to say like, hey, can I use these headphones or something like that. I'm retrieving search results, which are question answers, based on a match to the question. Makes sense, right? This is my index. There's nothing special about my index, just the default pipeline for search has to be that RAG pipeline, right? I picked stuff from earbuds, headsets, diffusers, mattresses, MP3 and MP4 players, sheets and pillowcases. Again, there's about 100 different categories of these questions. I don't think it's useful to try to show you a question. So what this piece of code does, it's just a quick loop. It uses the client. It creates a set for line by line, reads the JSON from the PQA data. I did aggregate all the answers. With the plugin, you can't actually point at an interior field, and the answers are all nested, so I had to like pull them all up. That's all I did there. It just sends them, 5,000 from each. And then it's just a quick loop. So I create a conversation context, and these sleeps, my laptop is too fast talking to itself, and so the index doesn't settle fast enough, so I had to put in a couple sleeps. But then it's just while true, I'm going to send this request. So notice the query here is a simple query string with whatever you typed against the question text, right? And then we specify this generative QA parameters. The LLM model is Bedrock Claude. We pass in the question, we pass in the memory ID, and then we get a response. And if the internets will favor me today, pay no attention to the prior one. It's not like I tried this before. Okay. Is that too small? If you can't see it, raise your hand. No, everybody can see it, good. Okay, so it's indexing. By the way, it's running locally on my laptop. OpenSearch is. So I have a couple of questions that I tried. And it's funny playing with this. The plugin is actually doing lexical search. And that means that when the questions are a little bit more specific, we get good answers, right? So the question was, where is it? Yeah, the question was, my demo didn't work. Darn it. Well, based on the information, it looks like I didn't get back search results. Let's try that again. And maybe it's because I have an extra space in there. There we go. All right, so for some reason, the first one glitched out, probably again, settling. So the question is, are the H251N, PN 70 with this number good at filtering sound, right? Remember, I'm coming to this with an information goal of figuring out an answer to one of my questions. So I'm using the LLM to generate an answer. These are the search results that come back. Some soft twin sheet set, Skull Candy, P54 Xbox, hotel luxury bed sheets, HyperX cloud gaming. A bunch of stuff comes back. And then that's part of the context that goes to the LLM. And then we get this response with, thankfully, a stack trace. Anyway, we get this response based on the results. Does not seem like they have active noise cancellation or are particularly good at filtering external sound. Reviews focused on quality for music or gaming. Some key points, right? So I got the answer to my question. All right, given that we're crashing out here, of course that didn't happen when I tried it before. Okay. So that's all bundled into OpenSearch, and that gives you, again, an example of how I can specify a query. It's like I get an answer for that query. So I wanted to talk for 1 second about where we go from here. So one thing is, as you look at the overall full stack in terms of search, right? We have on the top, we have our source and processing. This is a key step. You can't retrieve what you didn't put in, right? And so how you put that data in and how you structure it controls how you're able to retrieve it. We have not only building embeddings on the way in, we also have chunking, so figuring out what are the relevant pieces of the information and how do I cut it up to make them matchable. We have enrichment, maybe stock information for an e-commerce site. We have all kinds of other information that we maybe gather together in that document. And then it goes into some canonical store. Usually the canonical store is driving the UI or is driving the application and interactions. On the query path in the center, the query comes in, and there's a lot of things that we can do with that query. We know potentially, how did this person interact with this data before? We can have preferences in terms of brand or in terms of all those kinds of things. So potentially, we're going to rewrite that query. We then pass it through someday algorithm selection that says how concrete, how abstract is this query? What are the right fields to match? What are the right vectors? All of that stuff. You have your normal analysis for your query, your matching for your query, ranking for the query, re-ranking. This one comes up a lot. Like and especially in sort of LLM or semantic search context, you want to use the re-ranker to make your results better. What often happens is you didn't retrieve this stuff in the first place. Your ranking is actually not producing the objects. Your matching is not producing the objects. So you can't re-rank what you didn't already rank, is my point. And so this whole chain ends up with some list of search results that go to the front end. From there, then, you want to actually take those results and track what users are doing. Did somebody click on the third result? That's kind of less good than somebody clicking on the second or the first result. But you want to capture all that stuff. You want to know what people are clicking on if it's e-commerce, or even if it's just information retrieval. You're going to take all that behavior, you're going to post-process, you're going to roll that back into not only your query, but also use it to enrich your documents so that you know this thing is hot, it's trending, that kind of thing. So there's some pieces that are happening right now. We're working on user behavior insights, which is making it easy for you to send the interaction behavior to OpenSearch. As I mentioned, algorithm selection is coming. That's kind of on the frontier. People are doing that. Bringing it to OpenSearch has to happen. Re-ranking selection, we have re-ranking, but actually figuring out which re-ranking algorithm to use and which one is actually going to give you the best final results, still to come. So I wrote a book. A lot of this talk is directly driven from that book. I will be sitting at a desk out there handing them out. So if you want a book, come get a book. And apart from that, for me, it's always that language connection. Like, how do we speak and understand? What's come in terms of language processing has made it possible to do that semantic matching that makes natural language a means of interacting. So how you interact with your information is actually changing and will continue to change. So that's it for me. Thanks very much.